Hello everybody, it's Amel, and today I'm going to teach you how to solve the first bad version problem. You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n versions, 1, 2, all the way to n, and you want to find out the first bad one, which causes all the following ones to be bad. You are given an API bool is bad version, which will return whether version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. So here they give you an example. n equals 5. That means that you have 5 versions. And version 4 is the first bad version. So you need to minimize the number of calls to the API to find that version 4 is the first bad version. As you can see, you try 3, but it is good, so it returns false. Then you try 5, it is bad, it returns true. And when you try 4, it returns true, so this is the first bad version, which is between 3 and 5. So how can we solve this problem? The naive approach is to use a linear search. So we can iterate from left to right. Every time we see a number, we call the isBadVersion API or the isBadVersion function. But this approach is going to take linear time, big O of n time. So this is not a good approach. So how can we improve the time complexity? Well, this is a search problem. We are trying to find the first bad version. So because this is a search problem, we can use binary search. As you can see, all the elements are sorted from 1 to n in ascending order. So I can use binary search to find the first bad version. So without further ado, I'm going to show you how to write the code. First, the first element is 1. So my left is going to be initialized to 1, and the last element is n. So right gets a value of n. Then I will have a loop. So while left is less than right, I want to have this condition that left is less than right because I want to be looking at two different numbers, at two different versions every time. If I have only one version, I will break out of the loop. So while left is less than right. Then in binary search, we find the middle point. So we can say integer mid gets a value of left plus right minus left divided by 2. And this is to avoid overflow. Some people used to do left, they used to do left plus right divided by 2. But this is not good because you can have overflow errors. So it's better to use left plus right minus left divided by 2. So we find the middle point, and then we check if the middle point is a bad version. If is bad version mid, that means that, let's say number 2 is a bad version, for example. That means that this could be the bad version, or the bad version, this could be the first bad version, or the first bad version could be to the left. But all this part here, we can discard. We can discard it because it cannot be there. So what we can do is say right gets a value of mid, because this could be mid, could be the first bad version, or it could be a value before mid. So we say right gets a value of mid because it cannot be here. So we eliminate this right part out of consideration. And that's the power of binary search. Else, if mid is not a bad version, it means that mid is a good version. So because it is a good version, let's say that 1 is a good version, or let's say that 2 is a good version, then as an example, then the bad version, the first bad version, cannot be in the left part. It cannot be 2 itself, and it cannot be any value before 2. So we can eliminate the entire left part. So we can say left gets the value of mid plus 1. It cannot be mid itself, and it cannot be any value before mid. So we just eliminate the entire left part by setting left equal to mid plus 1. And then by the end, we know that the first bad version has to be left. I run the code. I will submit my solution. This is working perfectly. So as you can see, the time complexity is big O log n because we're using binary search. The space complexity is big O of 1. When we were using the linear approach, the time complexity was linear. But in this case, using binary search, we took advantage of the property of the input. And the property is that the input is sorted in ascending order. And we were able to find the first bad version by reducing the search space in half every time. So that's why the time complexity is big O log n. If you like this video, please press the like button. Don't forget to subscribe, and see you next time.